Welcome to module 18. In this module, we will learn about the relationship between thermodynamics and sustainability and then go through the method of energy analysis. So, to begin with, the motivation behind this module is why do we need thermodynamics based life cycle analysis, or why do we need to include thermodynamics in our sustainability analysis. Since energy is a key aspect of the way we function on this earth, and it's a key currency that is required to sustain our activities, energy becomes an essential part to think about sustainability of any activities that we are performing. So, when we go to a larger view of earth, we understand that earth is not a dormant dumping ground or stock place. So, we know that in lot of the sustainability analysis, we do an assessment of the total life cycle emissions or total life cycle resource consumption, which is the material view or the impact view of interaction of our technological system or human system with the nature. However, we know that earth is also a dynamic system. It responds to the changes we make. Whatever we are putting energetically, it changes the earth. A very simple example is the touch me not plant. So, whenever you touch it, it responds to your changes. And whenever you are actually interacting with the environment, there are subtle changes that are happening. However, we are not able to observe it so quickly. The theory behind this is Gaia, which says that earth is a self-regulating complex system, and whatever ways the human society or the technology is interacting with the earth responds to that. And in a sense, our ecological changes and our climate change is a response to the effect that human societies have created on this system for long. This means that if we are doing our assessment and we are only looking at the emissions and resource consumption as a flow from ecosystems or to ecosystems, we are possibly missing a big piece of understanding of how we are affecting the earth. And we know that LCA and industrial ecology are systems tool that has the motive to include earth systems or ecological systems in our analysis. And the easiest way to do that is to consider energy, because energy is the common currency between the ecological systems and also the technological systems that is required to sustain both of these systems. So, even for ecological systems, whenever there is a transformation happening, for example, photosynthesis, we are converting solar energy into biomass, and that is done by the nature. So, whatever the energy assessment or energy availability is there in the ecological system, that will affect how much photosynthesis happens and how much biomass is available for human consumption. So, whenever we are extracting energy or we are dumping energy in the environment, there is some response of that ecological systems to the energy flows. Hence, energy flows become a very important parameter or a metric in the sustainability assessment of the technological systems. Now, it depends on the system boundary. If we are only looking at the technological systems, of course, energy is just an input, and we understand how well are we using that energy. So, we look into assessments such as energy efficiency. Then we also want to understand how well we are converting the energy into useful product. That is the useful use of useful energy that is available for use. And then the last is how the energy assessment or how energy is interacting with the ecological system, and what is the role of ecological systems in providing that resources, that accounts for also including the ecological systems in contributing to the energy flows for sustaining our activities. In this module and the next module, we will go through the methods that will focus on using energy as a metric in the sustainability assessment for technological systems and also for the interaction of technological systems with the ecological systems. So, let us move forward. So, the types of thermodynamic analysis that we will focus is first is energy analysis, then we will go through the exergy analysis, and when we go to exergy analysis, I will introduce what exergy is with the second law of thermodynamics, and then we will go to the emergy analysis. So, let us get started with energy analysis. So, in energy analysis, there are three things that we consider: energy analysis for processes, life cycle energy analysis, and then we will look at what are the limitations of energy analysis. So, to get started with energy analysis for processes, we consider the natural flows. So, if you look at a processes, there are inputs and outputs. So, if you remember, whenever we started with an LCA, we looked at the inputs and outputs. So, inputs could be the raw material and the outputs are the products or co-products or the waste. Similarly, for the energy flows, we will first look at what are the inputs and outputs in terms of energy. So, one input could be the feedstock energy, which is the energy content of the resource that is being extracted or used for conversion to product in a process. This could be the energy in the coal or any other component that has the embodied or the available energy in that. Then we have what we call as the processing energy or process energy. That is the energy that is required on top of the feedstock to actually process. So, for example, if you are going to process coal into some product, then you might need additional energy to just process the coal into a product. So, that is the process energy. Then we have the product energy, which is the energy content of the product, and you can see that some products may not have energy in it, and then we will go to the exergy analysis for that. But for now, we will focus on the products that have energy content in their in the product itself. And then we will have waste energy. It could be just that energy is being dissipated, or it could be some stream that has some energy content and it is not part of the product, but part of the waste. So, you have from the inputs and outputs 4 flows that we look at. One is the what is the feedstock energy. Second, what is the processing energy for the process. Third, what is the product energy, and then last, what is the waste energy. Once we have quantification on all of these flows, we know that energy can neither be conserved nor destroyed in the process. So, from that we will have the first law of thermodynamics used to actually test whether your process is following the first law of thermodynamics or not, which means that your energy input should be equal to energy output. Your energy input is EF, which is the feedstock, EPF, which is the processing energy for the feedstock, EP is the energy of the product, and EW is the energy of the waste. Of course, if you have dissipation energy, you can include that as well, because there might be additional dissipation which is not in part of any flows, but it might just be the heat dissipation. So, once you have all of these flows that you map for your process, then we can go for the metrics that can be used. So, the first metrics that you might be aware if you have taken any engineering courses is the energy efficiency. Energy efficiency is simply defined as the ratio of energy content of useful products to the total energy entering the process. So, your eta is given as EP divided by EF plus EPF. So, your energy content of the product is what is the output, and that is the energy content of useful product. We do not include the waste energy or the dissipated energy in the energy of the product. In the denominator, we have the total energy input, which will be the feedstock energy. So, whatever is the content of the feedstock, and then the processing energy, what we are putting in additional to the process to actually process that feedstock into a product. Your efficiency is generally less than or equal to 1. Because none of the processes are fully efficient, you will generally find that the efficiency of the processes in our economy or in our technological system is generally less than or equal to 1. So, that is the first metric. What this metric gives is how good is the process in utilizing the energy and the energy content of the feedstock to convert to the valuable product. Of course, if your eta is closer to 1, it is a good process. From an energy profitability, which is an important thing for sustainability, the higher the efficiency of the process, the better it is. And we will see that when you calculate, you will be able to understand that which process is better in terms of energy utilization. So, you can of course relate it to the sustainability decision making, that if you have 2 different processes and you want to select which one is better from the energy sustainability perspective, then it is the one which has a higher efficiency of energy utilization. Next metric for energy analysis is the energy return of investment. So, energy return of investment is defined as EP divided by EPF. So, EP is your energy in the product and EPF is your energy for the processing. So, what this metric is telling is that we have a process and we have the feedstock which has the energy P, and we are investing additional energy of EPF, which is the processing energy, to convert it into the product. So, what that means is that your energy in the product is your output, and the amount of energy that you have additionally put in instead of the feedstock. So, we do not consider the feedstock, but just the additional energy, which is the processing energy that you have additionally put. So, you want to know what is the outcome of investing that much amount of energy in the process. So, that is what we call as energy return of investment. Of course, again here the higher the EROI, the higher the energy return of investment of a process, the better process it is. As we have to invest more and more energy to get the same amount of product, your EROI or the energy return of investment reduces, and that is not considered favorable. So, again from a sustainability perspective, if you are comparing a process with higher EROI is always better, and we would want to move the systems towards better EROI, and that may depend on identifying where you are losing the energy in the processing and then improving that process so that you are losing less and less energy. So, you are investing less and less amount of processing energy to get the same amount of energy in the product. And the last metric is very simple. We just calculate E net equal to EP minus EPF, which is basically that how much is your additional energy or the difference that you get out of input energy in the processing energy form. And of course, for process to be energetically profitable, we want higher E net and also higher EROI. But generally at the process level, we do not see EROI greater than 1, because what happens is that there is a lot of dissipation of the energy and we do not get everything into the useful product. So, let us do a quick activity now to calculate the metrics for the sustainability of the processes. Here you have a process that is processing crude oil to gasoline, and the process consumes 4 megajoules per kg of extracted oil. So, the fuel value of crude oil is 40 megajoule per kg, which is the feedstock, and the fuel value of the gasoline is 42 megajoule per kg, which is the output of the product. So, here I am asking you to ignore the waste. So, take time to calculate the efficiency, energy return of investment and net energy of this process, and the processing energy here is the 4 megajoules per kg. So, let us look at the solution. Whenever you have a problem like this, your first step would be to actually draw the process flow diagram or just the flow diagram of the energy inputs and outputs. So, here in this case, we have a process that is extracting or that is processing crude oil. So, our process can be named as crude oil processing. And we have the fuel value of crude oil is 40 megajoule per kg. So, we have to identify what is the feedstock, what is the processing energy and what is the product. So, our feedstock is the crude oil, which has 40 megajoule per kg, that is, and let us assume we have 1 kg of flow, and the fuel value of gasoline is 42 megajoule per kg. So, you enhance the product, and let us assume 1 kg is the output, and we have the processing energy is 4 megajoule per kg. So, the processing energy is 4 megajoule because we are processing 1 kg of crude oil into 1 kg of gasoline. So, this is the gasoline which is the product, and this is our crude oil. So, for efficiency we remember it is energy in the product divided by energy in the feedstock plus energy in the processing of feedstock. So, our EP is 42 and our feedstock is 40 megajoule and our processing is 4. So, that comes out to be 42 by 44 and your eta will be about 0.95. So, we are losing some energy which might be going into the waste, and we have of course ignored it, but you can see that your efficiency that with which we are able to utilize this processing energy to convert the feedstock into product is about 95%. Next, we can calculate energy return of investment. So, your energy return of investment is defined as the product divided by the processing energy. So, our product is 42 megajoule and we have 1 kg. So, that is 42 megajoules and 4 megajoule is your processing energy. So, your EROI here comes out to be 10.5. So, you can see that the energy return of investment is about 10 times, which means that this process is really good in terms of giving back the energy that we have invested in form of a product. And then the net energy, E net, is just simply the difference between the EP minus EPF, which is the processing. So, we have 42 minus 4 and your net energy is 38 megajoule, which means that we are investing or putting in 4 megajoule of additional processing energy and we are getting 38 megajoules net energy for our utilization. So, if this is an energy producing process, this is the value that we are getting out of that process. The higher the E net, the better it is because we do not have to spend so much energy to get the energy product out of that process. So, this is a very simple example that shows how we can understand the sustainability of a process in terms of energy flows, and you can have multiple processes. You can calculate the efficiency, energy return of investment and net energy to really understand the energy profitability of these processes. So, now let us move forward and let us see what we have to do when we have a larger system. So, instead of just a process, now we are going to look at the life cycle of the system. So, most of the time we have been in this course focusing on the systems view or holistic view with multiple processes interacting. So, how do we do energy analysis in those cases? So, the good news is that it is very similar. The only thing is that the calculations become a little more involved in terms of that now you have to do a life cycle level calculation instead of processes. So, let us look at the net energy analysis or the life cycle energy analysis for the whole system. So, when we go to the life cycle scale, we start looking at the energy network diagrams or the energy flows in the whole network. So, here if you look at this system, we have the energy flows to the industrial processes. So, in most of our LCA studies or sustainability study, when we are making decision about product life cycle or process life cycle, we have the different industrial processes. So, remember our process LCA, this could be multiple boxes which have the, so this could be let us say 3-4 different boxes of where you have the different flows interacting. So, this could be our system boundary of the process flow. And all these industrial processes are now interacting with the ecological system and producing economic resources. So, this is our Y, which is our, remember, the final demand, which is the product that is being made for the economic consumption. And then we have non-renewable resources, so which is mainly the fossil, and you can, so the N1 is mostly the flow that is going into the industrial processes. So, our industrial processes are processes or life cycle being analyzed, Then we have the economic resources, which is the other part of the economy to which we are sending the product. So, remember our system boundary that we made for LCA. Then we have N1, which is the direct input of non-renewable resources or the non-renewable energy resources to the processes. So, this could include anything like coal or gas or let us say oil, that is we are putting in the industrial processes. Then we have direct input of renewable resources, which is R1. So, in terms of energy, this could also be something like biomass that is being used for energy. So, that is another input of renewable resources from the ecosystem, and that is where we are extracting directly from the ecological system. Then we have N2, which is the input of non-renewable resource to other part of the economy. So, remember that we are not modeling some part of the economy, and that is where other non-renewable energy resources are going. So, that is N2. And then we have R2, which is the input of the renewable resources. So, some of the renewable resources can also go to the economic system, which is not part of our study. And then Y is our main product from the process. So, remember we had this final demand for our LCA or the final demand for our economic input output LCA. So, once you have this kind of network diagram in your view, that you can understand that the whole life cycle of your system is interacting with the economy and the availability of renewable and non-renewable energy sources that we are extracting. Of course, the waste is going in the waste box. So, this is what we call as Howard Odum's language, because this is derived from how the energy flows in the ecological system. So, Howard Odum was an ecologist who focused on the energy flows within the ecological system. And you can see that ecosystem is getting its energy from the sun. So, eventually lot of the resources and energy that we are consuming is coming from the solar or other forms of energy. And once you have defined the non-renewable and renewable part, you can combine them in terms of energy units. So, now that we have the network diagram and we have all the flows defined for our system, let us look into the metrics. So, we already talked about F is equal to input from economy to support our process. So, we did not talk about this feedback loop, but we will leave it for now, because when it comes in the feedback loop for the network diagram itself. Okay. So, let us look at the net energy analysis. So, in the beginning we saw that the net energy analysis is total for the process, it is EP minus the processing energy. Here in this case we call it the cumulative energy consumption for the life cycle, and what it is, it is the total energy consumed directly indirectly for making a product. So, instead of now making that difference, we are calculating it as total energy consumed, and it will only focus on the fuel used in the life cycle. So, anything like coal, crude oil, natural gas, electricity, but it might also have the biomass based energy resource, which is the renewable energy. And if we can perform this kind of analysis, which is the cumulative energy consumption for the life cycle at different scales. So, at the process scale, at the economic input output scale, or at the hybrid scale. So, we can follow the same mathematical framework that we have learned for the process LCA or the input output LCA and the hybrid LCA to do the calculate the cumulative energy consumption or the net energy analysis. So, here you can calculate E net as the fuel value of product, which is EY. So, remember it is the energy in the product that is being provided, and we have the CYEP, which is the which is mainly the total energy consumed, which is CN1P. So, mostly it is the cumulative energy for the non-renewable. So, N1 is your non-renewable and N2 is your also the non-renewable that is going in the economy. So, the distinction with the process here is that we have now a whole life cycle network and also the economy, the part which is not there included in the process. But when we calculate our E net, we need to calculate the total energy consumption, or what we call as the cumulative processing energy consumed. And here our cumulative processing energy is something that is going to the industrial processes, but also the economy. So, we can calculate the total processing energy for the whole life cycle. And then the E net definition is very similar to the process information. Then we can calculate the energy return of investment. For energy return of investment, we have fuel value of products divided by cumulative processing energy. So remember, we can calculate our cumulative processing energy with including both the non-renewable resources and renewable resources going to the economic and the in processes. And here we can just calculate the fuel value of product divided by the cumulative processing energy at the life cycle scale. Similarly, then we can calculate the efficiency, and here in the efficiency, instead of just the processing energy, we will also include the energy of the feedstock. So the difference between the energy return of investment and the efficiency calculation is mostly that in the denominator for the efficiency, we also include the energy of the feedstock. So for calculation of efficiency, what you would do is you will do the fuel value of products, which we can get from the actual fuel value for each of the product, which is Y, and then divided by the cumulative energy, and in the cumulative energy we have the cumulative processing energy, which is C by PE, and remember that it includes both for the processes and the economy, and then also the energy of the feedstock itself. So that can give us the efficiency calculation. Once you know, rest of the calculation for life cycle is very similar to our input output LCA or the process LCA calculation or the hybrid LCA calculation. All you need to do is calculate this cumulative processing energy rather than at the process scale to the life cycle scale. And we will see an example of doing this calculation for an input output LCA, and then it will become more clear. So here is an example of some of the energy return of investment for fuels. This is taken from a paper published long back in 2005, and you can see that the energy return of investment for crude oil in 1930 was 100, which means that to get 100 units of crude oil, we only needed to invest 1 joule of energy. But here in the crude oil in 2000 now has 20 EROI, which means that now if you invest 1 joule of energy in the processing of crude oil, you only get about 20 joules of energy worth of crude oil. And the reason being that as the crude oil resources are being depleted, the level is going down and you need to pump more and more height, and that requires more and more energy. So now per unit energy invested, you are only getting about 20 units, but back in 1930 when there were plenty of resources, you were able to get about 100. Similarly, for the coal, you can see the reduced EROI over the years, because now the coal resources are more sparse and not as dense unless we find new coal reserves or new energy resources. So now we have, for 1950 we have 100 EROI, and for 2000 we have about 80 EROI. Similarly, for gasoline, it's 8. Corn ethanol, you can see it's the renewable systems have a much lesser EROI, and that has actually worked against using biomass as a energy source, because the amount of energy we need to give on the life cycle scale to get 1 unit of output is actually much larger for the bio-based energy resources. And then the shale oil is about 3, which is okay, but it's also very less as compared to the crude oil and coal. And that is why I think still you can see why crude oil and coal are still the preferred energy source if you just think about the energy profitability or the energy sustainability of the systems. So now what we will do, we will do an example for calculation of energy return of investment on life cycle scale. So for this one, this is a simple table that we have already seen in our previous module. So this is the input output table of 2-sector economy, and the flows are in the terms of dollars. So remember, we had calculated the energy resource intensity. Here what you would need to do is calculate the energy intensity. So I would let's do this first problem of calculating the energy intensity vector for each sector, and take 30 seconds. Utilize the definition that we have learned earlier on the resource intensity to calculate the energy intensity. So, energy intensity calculation is pretty straightforward. So, remember our resource intensity definition was the total resource per unit dollar of output. So, energy input intensity will be energy input to the sector divided by total output. So, for sector 1, if I have to calculate the energy intensity 1, we have 50 megajoules is the input. So, we have 50 megajoules and the total output is $1000. So, your energy intensity is 0.05 megajoules per dollar. For second sector, our energy intensity will be 200 divided by 2000, and this is megajoules, this is dollar. So, this will be about 0.10 megajoules per dollar. So, now we have the energy intensity. So, if you remember our life cycle calculation, so we can now use these energy intensities to calculate the total life cycle consumption or energy consumption, which is used in processing for any final demand. So, when we say this is the energy intensity, which means that now we are fixing the energy intensity, that if we have to make product, let us say agriculture product or chemical product, then your sector 1, which is the agriculture sector, will consume about 0.05 megajoule of energy per dollar of output. So, if you have a new final demand, you can calculate the total life cycle through flow and then multiply by this energy to get the total energy consumed, and that energy is actually energy for processing, because this is energy input that is going into the functioning of those sectors. So, this is the processing energy, and if you know the value of the fuel value of the product, then you can calculate the energy return of investment. So, let us move forward, and now let us calculate the life cycle energy consumption for final demand of $100 and F2 of $50. For that, you are going to use the same table. So, now I would say our F1 is $100 and your F2 is $50, and what you need to calculate is the total life cycle energy consumption. So, let us take 30 seconds to do that calculation. Okay. So, let us look at the solution. So, I have purposely selected the same final demand that we have used earlier. So, if you remember, we have done this calculation as x star equal to I minus A inverse F. That was the Leontief calculation. So, when you have to do a life cycle calculation using input output model, you use the Leontief model. So, if you do that calculation, you will get back our value of $239 and $175. So, you can go back to the previous modules where you have the calculations for this model and the calculation for A matrix. Now, to calculate the total life cycle energy consumption or total energy consumption, which is the processing energy, we can use our E energy vector times the x star. So, our energy vector is 0.05 megajoules per dollar and 0.10 megajoules per dollar, and that will be multiplied by 239 and 175. So, when you do this calculation, your total energy consumption will come out to be 29.45 megajoules. That is the total energy life cycle energy consumption to meet this final demand. So that is the total life cycle energy consumption for the whole economy, which means it is the life cycle energy consumption to produce $100 worth of product from sector 1 and $50 worth of product from sector 2. Now let's go to calculation of energy return of investment. So now for this one, what you need to do is to calculate the energy return of investment for the given final demand, and now you need to make an assumption for the fuel value of product from sector 2 is 100 megajoule and there is no fuel value of product from sector 1, which means that the total value of energy output from the product that we are getting is 100 megajoule for sector 2 and there is nothing from sector 1. So, our total, so remember our EROI is going to the energy of the product divided by the energy of the or life cycle consumption, or what we called as EYEP, which is the processing energy for the product. So, your EP is going to be 100 megajoules because that is, we have assumed the fuel value from sector 2 and there is nothing from sector 1. So, sector 2 is chemical sector. So, it makes sense that it is making a product that has some fuel value, and our processing energy is what we have calculated from life cycle energy consumption. So, here the life cycle energy consumption we calculated was 29.45. So, our EROI will come about 3.39. So, our energy return of investment for this economy is 3.39, which means that if you have to make a product, you need to invest about, or when you invest 1 megajoule of energy in this whole economy, you get a value of product of about 3.39 in this case. So, that explains how we use the different metrics on the life cycle scale. You can also calculate the efficiency, you can also calculate the E net in this case. So, in summary, for energy analysis, what the simple energy analysis does is it looks at the flows that are related to energy products, and it utilizes the first law of thermodynamics by balancing the input energy equal to output energy. Of course, there is a lot of energy that is going to waste. So, our efficiency of the process is never equal to 1, it is generally less than 1. The closer it is to the 1, it is more sustainable. We can perform this energy analysis at process level and life cycle network level to calculate efficiency, energy return of investment and net energy. So, you will hear this word of energy return of investment a lot in the analysis of energy systems, where we want to know how much energy at the life cycle scale we have used, such that in the last example we saw that we have used about 29 megajoules of energy for processing for meeting the final demand, and then you can calculate what your EROI is for that particular processing energy. This is used, we can use this analysis to inform decision about improving energy use in the life cycle and also comparing the energy profitable in two different life cycle of products and even in the energy system. And this is mostly useful for systems where product has fuel value. If the product does not have fuel value, all we can do is we can calculate the life cycle energy consumption and say that one system is consuming more energy than another, but we cannot just make a decision about what is the worth of that product. So, that leads us to understanding the limitation of the metrics based on energy analysis. And that is that this energy analysis is mostly useful for processes that are related to products with the fuel value. If your fuel does not have products for energy use, then we are limited only in understanding how much energy use per unit product is being done and not really understanding the real sustainability challenges, because we are not able to distinguish between the energy profitability of the system. So, in that case, what we do is we move from the first law of thermodynamics to second law of thermodynamics, and what we start doing is, instead of just looking at the fuel value, we also start looking at the exergy flow, which captures the energetic role of even processes that are not for products for energy use. So, any product, let us say a pen we are holding, a pen will have some exergy. It will depend on the process that was used to make that pen. So, here even though our pen does not have a fuel value, we can use similar kind of thermodynamic analysis to test the sustainability of the process. So, in the next module, we will learn basic introduction to second law of thermodynamics, very quick review, and then we will get into the exergy based metrics and the logic behind using exergy to use for sustainability decision making in thermodynamic analysis. So, thank you for this coming to this module, and I look forward to see you in the next module.